Keynote. There we go. Okay. Good morning. Good morning. Morning, class. I'm just laughing. Whenever I see rooms like this, it's like I want to take a register. Bob isn't here. Where's Bob? Where's Bob? So thank you very much, first of all, to the organisers of NDC for inviting me. It's a massive pleasure to be back in Copenhagen. It's a city I really love. Denmark, I really love. I spent quite a lot of time in Aarhus, of all places, which is a great city. Any people from Aarhus in Aarhus? Been to Billund, of course. You have to go to Billund because reasons. And here I am in Copenhagen. Yeah, so thanks very much, Jakob and the rest of the NDC crowd. So my name's James. I'm going to be talking about this, team topologies, software architecture and complexity science. So I hope you enjoy it. But first, I thought I'd give you the background on my t-shirt. So this is an email I got from Jakob. Says, "Hi James, how are you?" I'm like, woohoo! NDC are back in touch, right? Excellent. Microservices workshop for Oslo and London. How about that? It's just, it's great. Maybe I could get back on the horse, after the pandemic, the after times. This is the next line. Sam Newman can't make it to NDC Oslo or NDC London. So we're looking for a replacement, any chance? I sent back literally this reply. So just to say, that says, Turing's dead, Martin Fowler said no, Sam Newman couldn't make it. Hi. So I'm wearing my t-shirt. Hi, I'm James Lewis. Morning. If you don't know who I am, I'm the other microservices guy, right? Sam got to write the book, but I got to go on a sleepover with Martin, where we wrote the original set of characteristics that we found for microservices. And in that, we said this. So we said we cannot say there's a formal definition of the microservices architectural style. Right? What we were trying to do with the microservices definitions or characteristics that we came up with is harvest a set of things that we saw organizations doing and being successful doing it. Right? So, for example, when we talk about componentization via services, Netflix at the time were talking about fine-grained service-oriented architectures. That was the name they were talking about. Dan North, who is now Daniel Terhorst North, he was at an investment bank, commodities trader actually, and they were talking about replaceable component architectures at the time. And the Guardian newspaper group were also talking about small services and so on. Come in, class, come in. There's a couple of seats at the front over here, actually. There's 3 here. So this is what we were sort of trying to do, is trying to look around and see what was working in the industry, what was different about the sort of period 2010 to 2012, where this massive sort of explosion in distributed system design was happening. Why was it working? Why was it successful? And we tried to come up with a limited set of characteristics, which are these. I won't go through them all, because you've probably seen these. Sam's talked about them a lot. We've talked about them a lot. But what this talk is about is not microservices per se. It's not software architecture with microservices per se. It's not about these characteristics. It's about my journey since then. It's about sort of 2012, 2014 on to now. It's about the things I've been thinking about in my head, the sort of ongoing journey, to kind of, what's the boldly go Star Trek thing, but the ongoing journey to kind of understand why is it that these were successful? Why has the microservices architectural style become the predominant architectural style for now, really? So that's what this is about. It's a keynote, so it's supposed to be big ideas. I hope you're ready for some big ideas. There's going to be some elephants, because why not? There's going to be some shrews, because again, why not? The Etruscan shrew is very small. There'll be cities, there'll be companies, there'll be teams, there'll be software architecture, a whole bunch of stuff. But it is quite an abstract talk. It's quite a sort of out there talk. So I remember when I worked with Dan North, we used to pair together at an investment bank in London. And he used to sort of talk to me about chunking up in abstractions. So, when you're thinking at the sort of level of methods or inside a class, you want to think about that level of abstraction. When you chunk up to sort of thinking about groups of classes, maybe in a namespace. You want to think about that level of abstraction. And then you want to chunk up again to groups of namespaces, maybe libraries. You want to think of that, and you chunk up again to maybe a service, and chunk up again to maybe a domain, bounded context, and maybe then you chunk up again to business capabilities. That's what this is about. It's about sort of chunking up. It's about seeing the sort of what levels of abstraction we might be able to think about that underlie these characteristics. So I hope you enjoy it. What we'll talk about first, though, is the fact that underpinning a lot of this is the thing I noticed, is this idea of decentralization, right? Of small things communicating via uniform interfaces and pushing responsibility for things like decision-making and governance and data management down to the people who know the most, so teams, down to individuals on teams, rather than having decision-making done in an ivory tower somewhere where you have to kind of wait for responses and all this kind of stuff. So, decentralization of data, pushing things like data mesh these days, that's the sort of the end result, if you like, of thinking in terms of microservices. Having data products owned by the same teams that own the microservices. So decentralization. So that's what got me thinking about the rest of it. But what I'm going to start with, as I promised, is this idea of team topologies. Now, it's early in the morning. It's earlier for me because, hour behind all that. Put your hand up if you've read team topologies. Put your hand up if you've even heard of team topologies. Interesting. This is going to be new for you then, which is great. So team topologies is a book written by two folks in London who are very sort of active and have been active members of the continuous delivery and sort of DevOps community in London. It's a brilliant book because what it does is it gives us, in DDD terms, a ubiquitous language to talk about how our teams work, how we structure our teams around building software, and the different types of teams that you can encounter when you're looking to build software and to optimize your organization for faster delivery of software, for improving flow. So that's what the book is. I've got a reference to it in a minute. I'll just give you a brief overview of team topologies. But first, I want to take you back a few years. My job is terrible. I fly out here, I do the keynote, I get a nice hotel, it's very nice, thank you very much, NDC. And this is a quote from someone I know at Amazon, AWS in particular. I was at a workshop on the lovely Caribbean island of Anguilla. So it was an open space, unconference in the Caribbean, which I go to roughly every year, or used to. Poor James, you're playing. Poor James in the Caribbean every year. But we were at this workshop, and there was an interesting group of people there that year, one of whom was Melvin Conway of Conway's Law fame. So Mel Conway, he's actually real. He does exist. He's getting on a bit, has to be said. He's sort of, 80 or so these days, but still very active in thinking. He's a really active thinker still around sort of philosophy of software and how to build software. But he was at this event. And we had a session one afternoon about Conway's Law and how we'd used Conway's Law. And there was someone from Netflix there who said, well, in Netflix, what we do is we sit teams according to Conway's Law. Right? So we have the UX team, they sit next to the platform API team, and then the microservices team sit behind that, and then we've got some ops teams sitting behind that, and all the way over there is Cassandra and that. Because the UX people don't really need to talk to the Cassandra people, right? So we optimize how we sit people in the building, very different, this is the before times, how we sit people in the building according to who they need to talk to most, right? So they optimize around Conway's Law. Conway's Law is this idea that your team structure will be reflected in the architecture that you build, or vice versa. The architecture, the software architecture or design of software is influenced by the structure of the teams of the people building it. So you can optimize for that. And Mel Conway, he's like, oh my God, there's this massive company in Silicon Valley. I wrote this paper in 1968 or something like this, and now they're organizing themselves according to this random paper. Which you think, it's like I just wrote this thing a long time ago. I think it was Build Stuff. It was in a couple of years ago. It was the first time he was invited, he came out of retirement to go to Build Stuff to talk. But there was someone else there from Amazon, from AWS, and they said something interesting about Conway's Law. They said this: the bigger we get, the easier it becomes to get bigger, right? So for Amazon, for AWS in particular, as they get bigger, it's easier to get bigger. As they add more products, it's easier to add more products. As they add more teams, it's easier to add more teams. In fact, to the limit, the guy said, we are only limited in terms of our scaling by the number of people we can hire, right? If we could hire everyone in this room, we could now then build another sort of 30 products, bang, right, without worrying about scaling effects. Thinking, well, that's slightly unusual, isn't it? But I'll take a step back from that, remember that. I'll take a step back and talk about organisational design briefly. So I think the goal of successful organisational design, right, is to optimise the flow of value. Right? Everything else is subordinate to that. Right? When you think about any organisation, whether it's manufacturing, whether it's retail, whether it's what we do in knowledge work, whether it's being a lawyer, it doesn't really matter. What you're doing on a day-to-day basis is optimising the flow of value from somewhere to somewhere else. Whether it's oranges from Seville to my tabletop at home so I can eat them, whether it's requirements from someone in the business's head into production where I can make money, right? Whether it's a legal case progression through the courts. It's about flow. It's about moving stuff through a series of steps, optimizing those series of steps. And a successful organizational design, and I would therefore argue for what we do, via Conway's Law, successful software architecture or enterprise architecture, the purpose is to optimize the flow of value. I really like this quote from Daniel Terhorst North. Our goal on teams when we're building software should be to safely and sustainably reduce the lead time to thank you, not to value, to thank you, to someone actually saying, I'm using your thing, thanks. Thanks for that, as opposed to, what the hell have you done here, teams? Sorry, did I just say that out loud? But that, three people laughed, that's good. Maybe I should have said, what the hell have you done here, Microsoft Teams, and then that would have got a bigger layer. But that does bring to the fore this idea of what is value. What do we mean when we say value? Well, as I say, it's stuff. Everything is valuable, right? When we think about lean manufacturing, what we talk about in a manufacturing process is going from something that has minimal value, raw materials, to something that has progressively more value as you pass it through a series of machines, creating widgets which get used by other machines to build better widgets, until finally you get a car. And the car has value, and you buy the car and you drive around, and it's great. But that's the stuff, right? It's just stuff moving through a value stream. And for what we do, the interesting thing about what we do is the stuff we do, the stuff we use, it's generally invisible. Right? This is one of the real realizations that I had reading a book called The Principles of Product Development Flow by Donald Reinertsen, is that the stuff we work on is invisible. If you're in a factory, right, and you're looking at stuff, you're looking at your machines, you know when something's wrong because stuff piles up. If a machine breaks, loads of stuff piles up behind it, right? Because you can't push it through the machine. How do we know that? How do we know if our processes are breaking? Well, what we do, and I'll do a talk on this tomorrow, is to use things like, Kanban boards to visualize the flow of stuff. That's really what we're doing when we're using, storyboards and this kind of thing, and writing user stories, is visualizing invisible stuff, invisible value. So basically, in my mind, physical stuff, knowledge stuff, they're pretty much the same. It's just information in one form or another, whether that's physical or whether that's digital or whatever it is, or in your head, moving through a value stream, getting progressively more valuable. You get raw materials, an idea, some iron ore, and then it turns into a thing, right? But then the question is, how long does stuff take? Now, this is from a client, I won't mention who. I work for a consultancy. I spend a lot of time with our clients. This is a value stream map of how their integration team works. So in the middle, does my laser work? Yeah, just about. In the middle, this is the integration team here. If you can see that. See that over there? Lasers. That's the integration team. That blue card there, over this side, this blue card there, that's writing code. That's it, right? Write code, it says on that card. This is we event stormed this. All the rest of it, all the rest of these process steps, all right, That's taking one thing, turning it into another thing, turning it into another thing, turning it into, sometimes reversing the process and turning it back into the thing it was before because that thing was broken, right, turning it into another thing. We've got a loop in here. The loop is brilliant. The loop is where two types of data architect who each had their own canonical model just went round in circles updating each other's model for about 4 weeks and then went, yep, we're done. Now you can write code, the little bit, right? That tiny bit, that's writing code. How long does stuff take? This is a 200-year-old organization. This is a very old company, right? This company's been around a long time. They've accrued processes. They've accrued a lot of stuff that they need to do. There's an integration testing step here. Probably at some point, it's a retailer. On Black Friday, 10 years ago, there was a problem. And so they said, we must do 8 weeks of integration testing or regression testing every time. And suddenly, if you want to make a tiny change, the fastest you can get it into production is 8 weeks. That kind of sucks, right? You sort of accrue all these processes and constraints over time. Back to team topologies. This is the book. So, Emmanuel Peiss and Matt Skelton. What they've done is, it's kind of a meta-study. They've taken all the sort of interesting work over the last, I would say, 15 years around teams and org structures and microservices and Conway's Law, and they've put it into one place. And we can use it as a great reference now for how we build our teams. These are the teams they talk about. They talk about 4 fundamental team topologies, stream-aligned teams. So a stream-aligned team is one, ideally, with a view of the customer, right, that operates along a single value stream. So if you think you're building a website, you might have a stream-aligned team around your checkout process or your basket, and they do everything end-to-end. You might have a team aligned around your catalog page or search, right? Independent teams building independent products, right, with their own view of the customer. You then have enabling teams, complicated subsystem teams, and platform teams. You can think of the enabling team as how do you make the best use of limited resources, right? So if you think about people like your awesome security folk, or DevOpsy people, or UX, user research folk. Those folk who you've never got enough to go around, right? There's never enough to have one on every team, as much as we'd like. You create these enabling teams and they can act as consultants out into the rest of the organization, and they dip in and out of teams when necessary. Then you have maybe, there's a really scary risk management system that only 4 people who know the mainframe know about. That's a complicated subsystem team. And then the platform team, platform engineering teams, whose job it is to make the rest of the teams go faster. They provide things like build and release pipelines, observability stuff. They might do chaos engineering, whatever it is. And these are pretty much the 4 team topologies that you need in an organization, in a software development organization, in order to go as fast as possible. So that's my first bit. So there's a Danish comedian in the UK, very famous in the UK, called Sandy Togsvig. If anyone has come across Sandy Togsvig? Yeah, some. She presents a very popular TV show called QI at the moment. And she tells this story about the first time she did stand-up comedy going back to Scandinavia. And she says, I did 20 minutes. And I thought it was pretty good material, she said. But everyone in the room was just looking at me. Blank. And I got to the end, and everyone gave me this massive round of applause. And I said afterwards to the organizer, what was happening there? He said, we really enjoyed it, but we were just too polite to interrupt you. And I thought that was, so are we all okay at the moment? Right? You're not being too polite to interrupt. Okay, good, right. So the next bit. The next bit is about software architecture. As I said, I think, in my mind, software architecture and organizational design, they are pretty much the same thing, right? When we think about team topologies, we think about how we structure our teams. We should be structuring the software the same way, right? That those teams are building. I'll take you back to this quote. The bigger we get, the easier it becomes to get bigger. To the limit, it's just hiring that's slowing us down at AWS. And then I thought, well, that's not my experience of most organizations, right? This is my experience of most organizations. Adding manpower to a late software project makes it later, right? This is the classic, Fred Brooks' paper, Mythical Man Month, where he talks about the fact that as you add people to a software project, you basically increase the amount of overhead from communication, you increase the number of communication pathways, and eventually the number of people, the amount of communication you have to do overwhelms the benefits you get from the additional capacity. That's this. Everyone knows this, right? This is like just the truth. So why is it that Amazon or AWS are able to get around this? So I thought, and by the way, I warn you, pseudographs are a thing in this presentation. So pseudograph number 1 coming up. For the data scientists, please don't shout at me. There's 5, how many, 6 points? 1, 2, 3, 4, 5, 6. 6 data points I could find on this. So when I was looking at this is a log graph of Amazon's size in terms of the number of people they employ versus the amount of revenue they're making over time. Right? And that straight line, we don't really care about that y equals blah. What we care about is that 1.15. That exponent means that Amazon are growing revenue faster than they should. Right? In general, I'll come to why in a minute, companies tend to scale their revenue less than the number of employees. So as you double the size of a company, you don't double the amount of revenue you make. That's just a thing. But Amazon are doing better than that. They're more than doubling their revenue as they're adding more people. If you think about it, adding one person means 1.15's worth of revenue as they add one person. So how can that possibly be the case? And the interesting thing is, when you go back to 2004, was it? Jeff Bezos wrote this memo around how we're going to work in the future in Amazon as we move away from big centralized databases, and we're going to move to these independent teams and so on. He said a few things. He said teams must communicate via interfaces. None of this talking to each other's database, ETL stuff. And admittedly, you're right, if there's people from Amazon in the room, I know it took about 30 years to get there. So but still, teams must communicate via interfaces. Those interfaces must be externalizable, which means we must be able to sell those to other people, right? And this is where AWS came from. Externalizable interfaces that their internal teams were using that were able to be sold on to us as consumers. And then finally, we're going to organize around smallish teams, right? Smallish teams building these services using externalizable interfaces, and that's how our teams communicate. And what I think these are, he came up with a number of forcing functions for improving the flow of work within Amazon, right? So limiting interactions to nearby teams. If I don't need to talk to you, why am I sitting next to you? I'll sit somewhere else. I'll just sit next to the people who I really need to talk to on a day-to-day basis. Isolating those teams, these externalizable interfaces, and then scaling by something called Dunbar's number. So in terms of software architecture, when Amazon moved from their big sort of centralized systems to what is now a sort of distributed system or set of distributed systems, and AWS followed that and made that sort of infrastructure available to the rest of us, that was because of these forcing functions to improve flow within Amazon, not for any other reason. It was to improve flow. They built a software architecture that enabled them to go, if you like, as fast as possible. But I did sort of say at the start that I wanted to talk about why, right? The underlying abstractions. And that's what the third part of this is about. So complex adaptive systems, CASs, complexity science. It's a bit early for it, but it's a fun topic, right? So complex adaptive systems, some of the ideas behind these were developed out of the Santa Fe Institute in New Mexico. A bunch of folk from Los Alamos, including like Murray Gell-Mann, a bunch of Nobel Prize winners, were intrigued by how from very simple things like atoms, you could get very complex things like jaguars. In fact, he wrote a book from the quark and the jaguar about this topic. How do you get stuff that's as complex as us from stuff that's as simple as our constituent parts? So here's a question. Or here's an interesting fact, rather. This is about mice and elephants. What do mice and elephants have in common? And us? Well, we've got roughly the same number of heartbeats in our lifetime as a mouse and an elephant. We also have the same blood pressure as a mouse and an elephant. We share these common factors, right? What changes between mice, elephants, and us, or mice, us, and elephants, is the rate at which our heart beats. Right? An elephant's heart beats really, really slowly in comparison to us. And our heart beats really slowly in comparison to a mouse. Right? And the reason that because essentially when you've got things that you need to conserve, like Kleibert's law, which is the number of beats per mammal in their lifetime, or blood pressure, something else needs to change, and it's the rate at which the heart beats that changes. What it means is that the bigger the mammal, the slower they live, the slower their metabolic rate. What this graph shows is as you double the size of a mammal, you don't need to double the number of calories that they need to take in order to survive. Roughly, an elephant needs about 75% of the calories you think it should need. As you double the size of a mammal, you only need 75% of the calories, because the metabolic rate of an elephant is much slower than us. Elephants don't get cancer, bizarrely. Their metabolic rate is so slow, their cells don't divide enough to really get the mutations that cause cancer. They operate really slowly. Metabolic rates in mammals, they follow this scaling law with this exponent of 3/4. As you double the size of a mammal, you only need 75% of the calories. Well, there's other examples of complex adaptive systems out there, like newsagents and giant supermarkets, right? I mentioned about doubling the size of a company doesn't double the revenue. Well, this is the figures from NASDAQ that were available. As you double the size of a company, you don't double the revenue. Within errors, this is about 3/4, so about the same as the scaling factor for metabolic rate. In mammals, a bit more research, it actually comes out at about 0.85. So as you double the size of a company, you get about 85% of the revenue you should, right? Based on figures from the listed companies on the exchanges. Another example, 2 cities that are roughly double in size. What do they have in common? Well, as you double the size of a village to a town to a city to a bigger city, giant city to a mega city, you don't have to spend as much money as you might think on infrastructure. So, for example, road length, petrol stations, restaurants, the amount of water pipes, this sort of thing, you don't have to double the number of water pipes as you double the size of a city. In fact, it scales roughly the same as organisations' revenue does, 0.85. So you have these 3 different examples of scaling laws from 3 very different things: cities, companies, and mammals, right? 0.85, 0.85, 0.75. But the key thing here is that they're less than 1. As you double the size of a thing, you don't double the size of the other thing. This is a quote from the book Scale. I've got the references at the back of this, at the end of this talk, so they'll be available. But Scale is a fantastic book, and Geoffrey West, the main author, he writes, quantities that do not change when other parameters of the system change, they play a special role in science. When we see in other words, when we see straight lines somewhere, we should probably go and have a look why and investigate what's going on, because there might be something underlying that we've missed up until now. And what these straight lines on those graphs mean, well, they've got a very particular meaning in economics. So in economics, you have different types of scaling, right? Different types of scaling laws. You have linear scaling. As you double one thing, you get double the other thing. This is kind of exponential growth. You then get sublinear. This is, by the way, I should point out, these are all log-log. You get sublinear scaling. As you double the size of one, you don't double the size of the other thing. And this is known as economies of scale. This is when our CFOs are banging on about, we need economies of scale, we'll get bigger and economies of scale, and we'll acquire that company because economies of scale. This is what they mean. This is technically what the economists mean by this. And underlying all of this is this idea of complexity, right? These 3 different types of complex adaptive systems. And the properties or characteristics of complex adaptive systems, there's basically 4 of them. The first is complex adaptive systems are self-similar, right? So they're built up from self-similar parts. We are built up from cells, and underline that, from atoms. Well, we are the same as a mouse or an elephant. We're built up from the same self-similar things, which are cells. Cities are the same. They're built up from the same self-similar things, houses with people in them. Companies are the same, people doing work. Self-organized. Complex adaptive systems are self-organized. There's no central coordinating agent that tells my body to grow into James, right? It sort of self-organizes into James over time. They're complex, like the whole is greater than the sum of the parts. If you put me through a blender, you couldn't put me back together again, right? That's pretty much, I mean, you'd have all the same stuff, but, James would not come out if you smashed the blender together into a James-shaped mold. Like, there wouldn't be thinking going on. Well, you might argue there's not thinking going on at all, but hey. And then this idea of emergent behavior. So if you run the same thing twice, if you have two similar scenarios, every time those scenarios play out, you're likely to get a different answer out. So emergent behavior. And underlying these four characteristics, mathematically, are three simple principles. The first one is this idea of fractal networks, a space-filling fractal network. I'm showing you an example of a hierarchical one here. Hierarchical fractal network. Think in our bodies, our circulatory system. That is a space-filling fractal network that takes nutrients from, basically, that allows nutrients to pass finally through from our blood into our capillaries to feed our cells. A space-filling fractal network. Water pipes in a city are a space-filling fractal network. You get a big water pipe at the, coming into, well, more than one, coming into a city. It branch down, till you turn on your tap. The pipe is the same size, and water comes out of the tap. Right? Space-filling fractal networks. And the same with organisations. Information pathways, information flow through organisations form this space-filling fractal network. They also, if you think about it, things like network connections and that kind of like information flow in terms of infrastructure you need. That's also a space-filling fractal network. Then we have this idea of invariant terminating units. So in our body, those are essentially capillaries and then the cells. In cities, those are things like the taps or the pipes that hit the taps and water comes out into your house. That's the house is the invariant terminating unit. In a company, it's basically people. I've been trying to get ThoughtWorks, rather than calling us consultants, to call us invariant terminating units. But actually they prefer meat bags, which is annoying, but hey, what can you do? And then the third thing you need is optimization of some sort. In companies and cities, that's market forces. That's how cities and companies operate, optimize. And in mammals, it's evolution, operating on evolutionary timescales. This feedback mechanism which turns us from single cellular organisms into what we are today, increasingly complex things. As I say, they're everywhere. Complex adaptive systems are all around us. The teams we sit in, the companies we work in, the cities we live in, and ourselves are all complex adaptive systems and a lot of the behaviors can all be described with those simple properties. So those scaling laws mathematically pop out just if you do the math on those three simple properties. But the key thing here to take away from this little bit is that hierarchies, anytime you see a hierarchical fractal network, it implies scaling with a power law with an exponent less than 1. It means every time you see a hierarchy, you don't get as much out as you might think. You don't double the thing when you double the other thing. Right? So anytime you've got a circulatory system, that means as you scale me, the circulatory system scaling means I don't need as many calories as you scale. Same with companies. As you scale a company, they don't need as many network cables randomly, but they also don't get as much revenue out. And that's due to the hierarchy. Basically, lots of things of different sizes, they're pretty much the same thing if you squint and look at them from 20,000 foot. Which brings me on to this idea of metabolism. Why does revenue growth slow as size increase? Why is it that metabolic rates slow as size increases? What is it about these things that cause that? And it's to do with the way the networks fit together, the hierarchies go from bigger things into smaller and smaller and smaller and smaller and smaller things. So for us, we've got a heart and an aorta, and then the arteries, they branch and branch and branch and branch until eventually they reach a capillary. And the difference between an artery and a capillary is size, and there's no pulse in a capillary, right? It's it's Lars. There's a continuous flow of of blood through the capillaries, whereas in the arterial system, you're pumping, basically. The heart is pumping blood through it. That's the difference between the invariant terminating unit bit and the arterial bit. If there wasn't a continuous flow, there wouldn't be time, essentially, for nutrients to leak out across the capillary boundary and for our cells to be able to use those nutrients, the oxygen, et cetera, right? It's down to the hierarchies. If you think about in a city, water pipes go from this kind of like pumped, basically you've got massive pumps somewhere pumping stuff through these big pipes until eventually you get continuous flow out when you turn your tap on. And this is down, interestingly, to how these fractal networks have evolved in us and how, well, basically, turbulent flow works. If you think about a messaging system, right, and you've got a consumer of messages, and that consumer of or two consumers of messages, and you've got one producer, right, and the producer is operating at a rate faster, or producing messages faster than the two consumers can consume them. What happens? The messages back up, right? Not able to process them fast enough. Well, the same thing happens, actually, in the circulatory system. We've optimized, evolution has optimized us, when you go from an artery of one size to two, they are exactly the same cross-sectional area. The reason being, if they weren't, blood would rebound off the boundary, putting back pressure up the circulatory system, up the hierarchy to the heart, putting pressure on the heart. This is where heart attacks come from. This is why plaque is so bad, right? When you narrow the size of an artery, you've no longer got the right cross-sectional area, you get turbulent flow at the boundary, impedance mismatching, and bang, you suddenly cark over and die, which is not very nice. And I'll come on to corporate, why companies die in a moment. But fundamentally, hierarchies and this flow of stuff through them, it's all about this idea of hierarchies, the flow of information through them, and these invariant terminating units at the bottom. Funnily enough, if you look at a blue whale and an Etruscan shrew, which is about the size of my thumbnail, they're the same thing. The only difference from a mathematical perspective is the number of splits in their arterial, in their blood supply, in their arterial system. The number of the depth, if you like, of the hierarchy. In fact, the Etruscan shrew is so small that it's pretty much got it's basically heart, aorta, artery, capillaries, pretty much. But you need to have at least one artery because you need to pump blood. And a blue whale's just got lots of them. So bigger animals, essentially, are more efficient because of the depth of the hierarchies of their fractal networks. The depth of their circulatory systems makes them more efficient. It means that they have a slower metabolic rate. It basically pops out. And this is due to impedance matching in the circulatory system. And that's driven by feedback from evolution. Bigger companies are also more efficient. So when people say economies of scale, it's actually a real thing. As you double the size of a company, you don't need to spend as much on infrastructure, on the things that are hierarchical, network cables, water pipes, all that stuff. Right? An office that's twice as big is more efficient than the one half its size. But they also, from an information flow perspective, they develop deeper hierarchies as they age. So as a company gets older, the length of time it takes information to flow from one place to another gets longer. And this is why the revenue scaling is the same. And this is driven by market forces. And they both slow down as they age as well. On to my next bit, flow. So I mentioned value stream maps earlier. So if you think about a hierarchy in an organization, in a company, and you think about a value stream map, it's pretty much a slice through your organizational hierarchy. It's a slice from where the work is imagined to come from and where the work ends up being done and put into production and earning money. It's a slice through that information hierarchy. And funnily enough, if you look at most value stream maps, lots of interesting things pop out. Things like queues, JIRA tickets. All right, I want to get a database. Let's raise the tickets. Okay, we're moving away from that age now, which is thankfully. But still, lots of tickets, backlogs, lots of queues. I need to go to the change request boards to get something approved. The architecture review board needs to approve this. Lots of queues of stuff. And what those queues are is the equivalent of plaque in your artery. Every time you put a queue into an information flow, what you're doing is you're deliberately pausing the flow of information. You're putting back pressure on the corporate heart rate, if you like, slowing things down. This book, Principles of Product Development Flow, talks a lot about why queues are bad. So Don Reinert, that I mentioned earlier, he's a genius. He's an awesome dude. He talks about the economics of flow, the economics of how of what we do, information, information work, knowledge work. What am I talking about? And in this, he talks about queues and why queues are bad. For example, the longer something stays in a queue, the longer your cycle time. If you've got a really deep queue, the thing at the bottom will take a long time to get into production, and so on and so on and so on. So, get this book, it's brilliant. The next bit is about corporate metabolism. So, as I say, to summarize rather, as companies scale, they add more and more processes and hierarchy, and things slow down. But we also deliberately block our corporate arteries by doing things like putting queues in place, deliberately stopping the information flow. So this is a bit of a sidebar. It wouldn't be a keynote without talking about Accelerate. So Accelerate, amazing book, one of the most, I think one of the most important books about what we do, again, that's been written in the last 10 years. This is the summary of the State of DevOps reports. Talks about how you can measure the health of an organization by looking at 4 key metrics. You can measure organizational performance just by looking at 4 key metrics, or you can see the trends in them. In the research behind Accelerate, they find, and I'm going to choose my words very precisely, that change request boards predict low organizational performance. They don't correlate with low organizational performance. If you have a change request board, it predicts you will be a low-performing organization. That's kind of interesting, isn't it? How many of you have got those? Architecture review boards, the same. They're predictors. So the interesting thing is, though, from Accelerate, what they give you is these 4 key metrics. Right? So mean time to recovery, there's a 5th now, which is reliability. But mean time to recovery, cycle time, change failure rate, and the number of deploys. And these things are the equivalent of going to our doctor and saying, I don't feel very well. They take your heart rate, take your blood pressure, take your temperature. These 4 key metrics are a sign of organizational performance. They're a sign of whether you're getting older as a company, worse performing, slowing down, whether your metabolic rate is slowing down, or whether you're going faster. So these 4 key metrics, they're leading indicators of organizational health, like going to get a checkup from the doctor. So we should work to, as Dan North says, we should work to safely and sustainably improve these things, right? Improve the lead time to thank you. But the problem is, any improvement is limited if you're in a hierarchy. Hierarchies will always limit you to growth that's less than exponential to sublinear growth. Companies die. Sorry to tell you this. Organizational mortality is the next bit. It gets better. Why do companies die? And it turns out they do quite a lot. The half-life of a company on the exchanges is about 10 years. So every 10 years, 50% churn on the stock exchange. In most stock exchanges, right? Half-life is about 10 years. You can't tell which ones, but statistically, companies die all the time. They get taken over, they go bankrupt, they get acquired. Why is it that companies die? Why do companies die, these complex adaptive systems, like we die, but cities don't? Well, it seems, and there's less research here because it's a bit less open. There's a lot of open research around cities and around things like biology. Companies are a bit more private, turns out. But it seems that if you look at the proportion of money you spend on R&D as a proportion of your overall budget, as you get bigger, you spend less than you should, if you like. In the same way as that, as we get older, as companies get older and bigger, as we get older, and in my case, bigger, I have to spend more energy on repairing my cells than I do on creating new ones, for example. Right? That's what aging is, really. And companies do the same thing, except it's manifests in a different way. It manifests as spending less on the thing that made them great to start with. They spend less on developing new products, less on invention, less on research and development, and more on sort of maintaining a steady state. More on reducing costs, this kind of thing. More on adding processes, adding constraints, until you end up with these giant value streams, which are giant hierarchies if you turn them like that. So what you end up with as companies age is these hierarchies, they grow and grow and grow with more and more constraints. But hierarchies, hierarchical organizations, they gain economies of scale for infrastructure, right? So this is a good thing. Our CFOs are right about this. An office twice the size is more efficient than an office half of its size. But they achieve sublinear growth in revenue. That's just the maths. That's just the physics behind it. You get 85% of the revenue as you double in size. And eventually they die, which sucks. But there is some good news, because there's a different type of fractal network that we can look at. And there's different types of scaling laws as well. So there's a different type of thing called returns to scale. Returns to scale is when you double the size of one quantity, you more than double the size of the other quantity. Again, this is log law. As X increases, Y increases by more than it should. And cities have both returns to scale and economies of scale. So they have returns to scale for socioeconomic factors: innovation, wages, number of professionals, crime, something that's very relevant at the moment, disease, growth and spread. It grows faster in a bigger city than it does in a smaller city, more than it should, if you like. So the socioeconomic factors, they display this returns to scale. Whereas for things like road length, as I said already, you get economies of scale. Right, this is why cities are so successful. As you double the size of a city, you have to spend less on stuff, less petrol stations, less roads, less lighting, less water pipes, but you get more out in terms of the amount of wages that people earn. All this socioeconomic stuff, you get more than you should. Oh, I've gone back rather than forward. Also, fun fact, walking speed also gets faster as you double the size of. They did research. MIT had mobile phone data, which they analysed. As you double, if you go from like a village to a town, people walk 110% faster. As they walk more 10% faster than they should, rather, in a town. Obviously in London we haven't all got like exoskeleton legs to enable this, but hey. So what is it that's driving these returns to scale, the superlinear growth aspect? It's this idea of small world fractal space filling networks, a different type of fractal space filling network, basically social networks. So if you look at your network of friends and family, that's a social network. If you look at the people you know in the city in which you live, that's a social network with more or less well-connected nodes and so on. And social networks are this driver. They're the thing that drives this type of loosely connected sort of social network drives superlinear growth. I mentioned, Dunbar's number earlier, 2 pizza teams. Well, 2 pizza teams is essentially around the Dunbar's number of about 15. There's more than one Dunbar's number. So this was based on a bunch of research around the number of people that you know, the number of sort of social connections you can sort of keep in your head, essentially, to paraphrase it. And they grow in different sizes. So the smaller one, number five is the number of connections that are your closest connections. So my nuclear family, it's awkward because I've got 6 in my nuclear family. So there's my wife and me and 4 kids. So it means I either love my wife less or one of the kids, and that's just maths. But hey, I haven't told them that. But then it scales up to the number of people in your closer family, and then your very close friends, and then your acquaintances, and so on. Dunbar's number, scaling by Dunbar's number, as Jeff Bezos sort of said, 2 pizza teams, because then you know everyone. We used to do this in ThoughtWorks. We used to open new offices. We've stopped doing it so much. Every time we got to Dunbar's number of about 150, 200, because that's the number of people whose faces you really recognize. Who I can say, hey, how's the golf trip? Or whatever you did, how was the Lego building thing you did? That would be me. Not Warhammer for me, but hey. But there's a number of people that you know really well and you can hold these conversations with. And every time we got to that number, we'd create a new office. We'd split off and start a new office. That's why we've got 3 in the UK. We've got, 8 or 9 in India rather than one big one. Because we're trying to scale around these social networks, the social effects. So what I'm trying to get to here is you've got options, right? In terms of how we structure ourselves, our organizations, and therefore our software architectures. We could structure around hierarchies, which are going to give you economies of scale, means you get less out than you might want, or we can structure around small world social networks, and then you get more out than you think. And if you think about it, it's kind of obvious because, how do you grow a small world network? Well, how do you grow a hierarchy? With a hierarchy, you've got to sort of add more layers, or you've got to squeeze layers. It's like computer science, data structures 101, where you have to kind of work out how to expand a kind of a graph structure. And it's just a nightmare, right? No one liked doing that. Much easier just to add a new node on the side, which is what small world networks do. In cities, you add a new suburb. You add a new little housing estate on the side. You convert some brownfield site into a new part of the city. You add stuff on the edge. And interestingly, you can measure the health of these networks by measuring something called the fractal dimension. So you can measure how crinkly the boundary is of a small world fractal network. It'll tell you how healthy it is. Detroit, when it was going through its sort of decline in the sort of 80s and 90s, how crinkly the edge of Detroit was, the fractal dimension, decreased. And now it's increasing again as it's becoming more healthy. We can do the same thing with our groups of friends, our Twitter, the people connected to us on Twitter and so on. So you add these bits around the side. So to summarize this bit, as cities grow, you get economies of scale for infrastructure. You don't have to spend as much as you might think on water pipes and so on. But you get returns to scale for socio-economic factors, like wage growth, number of lawyers. We always need more lawyers, right? It's a fun fact. We were in a dispute with a giant company once about being paid because reasons, and I think we couldn't really like progress legally because they had more lawyers than we had people. We actually had one person whose job it was for a whole year to try and get that cash, but anyway, that's another story. As cities grow, as I say, they gain these returns to scale. And they rarely die. Cities don't, in general, they don't die. There's some outliers, but in general, they don't. Fundamentally, you get 115% of the stuff for 85% of the cost. Who wouldn't want that? So, are there other companies organised? Are there companies organised around small world fractal networks? I would argue that ThoughtWorks is, classically. We have been for a long time. We're organised around these smaller units, Dunbar's number of about 150 to 200, and we split it up and we create newer offices when we hit that sort of number. You have to layer in other things on top, right? Coordination. So we all get together as a big, as the whole of the UK will get together every 6 months and create those connections like that and so on, but still. I would argue that Spotify is a canonical example of how of trying to build a company around small networks. These decoupled teams, teams or squads that are decoupled from one another in an organisation. It's essentially a social construct with coordination across with the guilds and chapters and so on. Some years ago, Valve, or an employee at Valve, leaked, apparently, their employee handbook, if you remember this. The fun thing is in that, they had a diagram of how they're organised, and it's a small world network. They said, we want to organise this way, because when we organise this way, we get to go faster, we get to do more stuff, we're more innovative, we create more products. They organise around small world networks. And finally, going back to those forcing functions from earlier, forcing functions for flow, forcing functions for improving how stuff gets done that Jeff Bezos put in place with the interface rules, the externalizable stuff, 2 pizza teams. Based on the data, this is the available data on revenue that Amazon have posted and on number of employees. Amazon seem to be doing it as well. As they double in size, they get more than double out. That's what the 1.15 in that means. So, as Amazon gets bigger, it gets easier for them to get bigger. The person I met in the Caribbean, this is what he was saying. And if you look at the maths, the reason it seems that they're doing that is because they're organised around these small world networks. These small teams that they spin up that are decoupled from one another. It has its downsides. I mean, if anyone's used APIs from multiple different Amazon products, like what? Everything's very different, right? They're not optimizing for consistency across API design, certainly. But they're able to add new stuff really easily on the side and then add new things that make use of those products as they go. As Amazon gets bigger, it gets easier for them to get bigger. So coming back to team topologies and software architecture. Team topologies, we've got these 4 fundamental topologies. Optimizing around flow, optimizing around creating teams around small world networks. Small teams aligned along value streams with direct line of sight of the customer, independent from others. You'd be pleased to know I've nearly finished. There's a lot of maths for this time in the morning. I said at the start, this has been my journey over the last sort of 10 years or so, trying to understand what the underlying principles behind microservices and why they're successful. And I think we found them. I think this is what they are, right? I think it's the idea that we're creating decoupled teams, cohesive around certain things, business capabilities, domains, and DDD terms. I guess, yeah. Decentralizing, pushing governance down to the people who know the most, rather than have to ask people who, in their ivory towers, rather than going up the hierarchy. Have what you need within your team. I think these sort of underlying principles sort of explain why microservices have been successful. And I think team topologies are basically a handbook, a guidebook, and a ubiquitous language for us to be able to talk amongst ourselves, which is what that's for, right? In order to discuss how to structure our organizations to improve flow. So social network effects imply super exponential growth. Hierarchies imply the opposite. Think about forcing functions for flow in your own organization. Think about how you might take advantage of some of this research. This is the research. There's lots of it. They're great books. And there's the original papers listed there as well. So that's me for today. Thank you very much for listening. You've been great. Thanks. And there's no time for questions, so go get some coffee before the next one. Thank you.